In this video, we're going to look at the final topic in sampling and estimation, which is how to calculate approximate confidence intervals. We're going to start by looking at how these confidence intervals are calculated, and then we're going to look at how they're actually interpreted, because it's a little bit different to the other areas of study. And then finally, we're going to look at the key questions that are asked about them in exam conditions. For those who don't know me, my name is Chris Iannazzoni. I used to work as an engineer for a defence company, and I've since left that to start a career in tutoring. I make these videos so that VCE students can do the best they can in math methods. With that out of the way, let's get into it. The formula for calculating an approximate confidence interval is detailed below. Don't worry, this appears on your formula sheet, you don't have to memorise this. You'll see that it's actually slightly different to how we would calculate it for the other areas of study. But there are some similarities. For example, the confidence interval is still centred at the mean, which for us means p hat. And it's still separated by a certain number of standard deviations away from the mean, where z is the number of standard deviations. And also, like the other probability types, the 95% confidence interval is the only one that we care about. There is a slight nuance to interpreting approximate confidence intervals for this area of study. Normally, we would think of a confidence interval as just some percentage likelihood that your outcome will fall between some lower bound and some upper bound. For example, a 95% confidence interval for a type of screw might be between 24 and 26 millimeters, where 95% certain that our length of screw is going to be somewhere between 24 and 26 millimeters. Confidence intervals in sampling and estimation are taken with p hat as the center. But here's the issue. P hat is a constant value for any given sample. It can't range. For example, if I sample 100 people and find that the proportion of people with blue eyes is 30 out of 100, then that's my p hat value. It doesn't change within that sample, it just is that constant. So to demonstrate this, let's take another sample of 100 people. This time I find that our proportion is going to be 28 over 100. If I keep doing this again and again and again with different groups of 100 people, I'm going to get a certain spread of outcomes. And if you plot those on a graph, what you'll find is that those outcomes are approximately normally distributed. The most common p hat value is the best estimate for the true population proportion. So what we're actually doing by calculating an approximate confidence interval using a given p hat value is we're 95% certain that the true population proportion that we're looking for is going to fit within our interval. Calculating the interval is actually a lot easier. It's just plug and play into the equation. This example here had a survey of 1,000 people, so n equals 1,000. We're told that 55% of people in the sample exercised regularly, so p hat is going to be 0.55. All we have to do is use that information to calculate our approximate 95% confidence interval. The only thing that's a little bit weird is that they expect you to use z equals 1.96 rather than z equals 2 like you would have been used to in the other areas of study. I don't know why they insist on such additional accuracy, but it does appear in the study design, and it doesn't even show up on your formula sheet either, so it's something that you have to put in your bound reference. Either way, once we know all those variables, we're just going to plug and play and then simplify. These are pretty much always tech-active questions. The one time that this has shown up in a tech-free environment, they've gotten you to use z equals 2. An alternative way to calculate these confidence intervals is to use the CAS inbuilt functions. On TI Inspire, this is located under Statistics, Confidence Intervals, and then one prop z interval. You'll just have to be mindful to convert your p hat value into an equivalent discrete number. On the Casio, it's actually located on the Statistics window under Calc Interval. From there, you're just going to select one prop z interval and then plug in the parameters as we discussed earlier. Once you hit Next, it'll populate the upper and lower bound that you need. Sometimes you'll be given an already solved interval and you'll have to use that to calculate what p hat and n must have been from that interval. In all of these cases, you're just going to start by calculating p hat by finding the midpoint of the interval. Remember, all confidence intervals are centered at p hat. Once we have p hat, all we're going to do is sub in all of the values that we know into the confidence interval equation. We've actually got two choices here. We can use either the upper bound or the lower bound. If you choose the upper bound, it's going to be p hat plus 1.96 standard deviations. And if you choose a lower bound, it's going to be p hat minus 1.96 standard deviations. All you're going to do from here is rearrange to solve for n, or, in this case, use the CAS because it's tech active. If this was tech free, the question would ask you to use z equals 2 to make life easier. One question that comes up somewhat often is to determine the effect on the width of a confidence interval by changing the value of n. This question here is asking us to figure out what happens to the width of the interval when we use a 4 times larger value of n. The fastest method of solving this would be to do it proportionally. We know that the width of a confidence interval is directly proportional to the standard deviation terms either side of the interval. Since to create our interval, we just start with our p-hat and add and subtract our standard deviations either side. So the width of a given confidence interval is just 2 times the standard deviation term. So in this case, 2 times z multiplied by the standard deviation. Now, to see what happens, we're going to replace n with 4n to see how it impacts the width of our interval. To make it easier to compare, what we're going to do is take that common factor of a fourth out of the square root. Just make sure that you square root it on the way out. And after simplifying that expression, we can see that the original width is 2 times larger than the new width. Hence, the net result of using a 4 times larger value of n is going to be a decrease by a factor of 2. If you found this video helpful and would like to see more, I actually have all sorts of additional resources available for free on my website. Just click the link in the description and you can access them here. And if you'd like my personal help, then consider signing up for the tutoring program. I offer the first 2 weeks free of charge so you can get a feel for whether or not this will be a good fit for you. Otherwise, I'll see you in the next video.